Let's prove this identity using mathematical induction for all n greater than or equal to 1. Now, for some references, there are different styles or ways to prove this using mathematical induction, but it all boils down to just simple 3 steps. The first step here is we are going to check whether this identity is true when n is equal to 1, as this is the first integer expected on our identity. If this is not true, then there's no need for us to proceed to steps 2 and 3. Now, let us try to check both sides. So our left-hand side is just this quantity here, the first term. You will have 1 times 2. The result here is 2. Let's check if the right-hand side is also true to be 2 with this expression if n is equal to 1. So simply substitute n as 1. 1 times 1 plus 1 times your n is 1 plus 2 all over 3. This is equal to 1 times 2 times 3 over 3. With this, we have here a result which is 1 times 2 equal to 2. This is our right hand side. And we have shown that both sides will have the same value when n is equal to 1. So with this, the left hand side and right hand side satisfies the first condition. Now let's proceed to our second step. Here, we are going to assume that n is equal to k, which will be very important as we proceed deeper on this step. That would mean, instead of n, we'll be using k. So our identity, 1 times 2 plus 2 times 3 plus 3 times 4 plus plus, instead of n, you will have k times k plus 1 is equal to the identity using k. We have k times k plus 1 times k plus 2 all over 3. Okay, so we are now changing or assuming that n is equal to k, where in this case, we are thinking that n or k is the largest integer that we could try for this identity. Now, part of this step is, what if we assume another integer but greater than n, or in this case, k? So an integer greater than k, just like an integer greater than 5 is 6, an integer greater than 107 is 108. So if k or n, again k, is the largest integer, the next integer larger than that is actually equal to k plus 1. And with this, we are going to add that same integer on both sides of our equation. So we'll have this form. For our left-hand side, you have 1 times 2 plus 2 times 3 plus 3 times 4 plus plus you will have the original k times k plus 1. We will be adding an integer here which is k plus 1 larger than k. But don't just simply add k plus 1 here, okay? This is wrong because the definition of all the terms on your left-hand side is expressed in this manner. It's not just n, but it's a product of n and n plus 1. So how do we make it correct? We're going to do it like this. We're going to copy, instead of k here and k here, we will have k plus 1 as the next integer. So you will have this first k will become k plus 1 as we treat that. And then the second k will have this form. Instead of k, you will have k plus 1, and then you still have plus 1 here. Okay? So this is the new term on our left-hand side, considering a larger integer than k, which is k plus 1. Let's not simplify this in the meantime, because if we are going to add that to make sure that we still have an identity, we will have to add this on the right-hand side using what is this expression. This was actually this form here. So you will have k times k plus 1 times k plus 2 all over 3. That is again this original form in terms of k. But since we are talking about identity and we are adding this term, let's also add that term, okay, here to retain equality. Okay, so there's no denominator, or we have the denominator 1. Let's not simplify this as mentioned, as we are adding the same, but we will take note of this because we are going to return on this expression later. Okay, now let's proceed to our third step. the third step. The third step now is when n is equal to k plus 1. Our first step is n is equals to 1. Second step is assuming n is equal to k. And this time is n equals k plus 1, which is different to this because we're adding a new integer here. Here, we just simply need to substitute k plus 1 to your n on our right-hand side definition. Supposedly, our right-hand side definition is actually n times n plus 1 times n plus 2, that's correct, n plus 2 all over 3. But since we substitute k plus 1 to n, this is what will happen now. You will have n is k plus 1. Then you will have k plus 1 plus 1, because this is our k plus 1. Then our n plus 2 will become k plus 1 plus 2 all over 3. Again, we're changing all n by k plus 1 according to this third step. So that you will not be confused with this, let me erase this one here. Okay? Or again, let's go back. Again, this is what will happen to them as we change n is k plus 1. Then again, I'm going to erase this so that you will not be confused with the two expressions. And probably move this up here. Alright. So I am now done moving that. So this is now the right-hand side of the third step. Okay. Now, the goal for our mathematical induction is this. The right-hand side of our second step, where we introduced an integer larger than k, which is k plus 1, expressed in this form following a definition of all terms on the left-hand side, this right-hand side of the second step must be equal or equivalent to an expression on the right-hand side of our third step. In short, your goal is simply like this. The right-hand side of your second step must be manipulated in order for you to reach an expression similar or equivalent to the right-hand side of the third step. And we're going to show that here. But since both expressions are difficult to look at, and it will be difficult for the right-hand side of the second step to reach an expression similar to this, there are some references who will not do this, but I advise that you can further simplify first your right-hand side of the third step. Not multiplying the rest, but just simply removing these grouping symbols here. So you will have k plus 1. Then, as you add this, you will have an expression of k plus 2. And as you add this, because just simply addition, k plus 3 all over 3. So instead of targeting this type of form, simply target this, which is easier to look at than the first version. So again, let's target this. This is the right-hand side of the third step, using the expression on our second step. Okay, the expression of the right-hand side of our second step is k times k plus 1 times k plus 2 over 3 plus the quantity, this quantity here, the thing that we added earlier, that's k plus 1 times the quantity k plus 1 plus 1. Okay, so our goal is again this one here. This is our goal. This is what we will be applying and using all necessary and appropriate algebraic operations. Let's not multiply that because it will make our forms more difficult in the meantime. So you will have here k plus 1. As you add this, you will have k plus 2. Sorry, k, that's parenthesis. I would like us to come up with an LCD 3. So this is just the same numerator because we have the same denominator of 3. So you will have here, you will have k plus 1, and k plus 2. But since the denominator here is 1, you have 3 divided by 1 is 3, so you will be adding a constant multiplier 3 for your quantity k plus 1 and k plus 2. Because if you're going to look at this, you can cancel it out. You're just simply returning to what is the original form. So you're adding a factor of 3. Now, again, let's not multiply this because we could see that there is k plus 1 and k plus 2 on both terms. You can simply use the factoring. So you're going to factor k plus 1, k plus 2. What remains now on our first term, this one here, is just k. And as you factor this, what retains on our second term is just plus 3. And they're all over 3 by simply factoring k plus 1 and k plus 2. This is the right-hand side of the third step. And do you know what is this? This is similar to the simplified form expressed earlier on our third step, the right-hand side of the third step, the product of k plus 1, k plus 2, and k plus 3 over the same denominator of 3. See that we simply end here instead of expressing in this form because we already simplified our third version of right-hand side into this form. And this comprises the proof of this identity to be true. The steps again, you are going to assume n is equal to 1 and show that both sides have the same value. If it is, proceed to step 2, assume that n is equal to k, and then introduce a new integer that will be added on both sides of the equation following what is really the appropriate definition of all terms on the left-hand side. Then, your third step is when n is equal to k plus 1, substitute to our original right-hand side, and then the goal here is from your right-hand side of the second step, this one here, we'll have a form similar to the right-hand side of our third step, applying all necessary mathematical and algebraic operations, and at the same time, it would be helpful for us to simplify the third version as well. Okay? Thank you very much for watching.